Okay, I'm going to start with just a couple bits and pieces, some loose ends, if you will. And I like these shorter ones because we can upload them to Moodle, and I think that works better. Photodetectors, we've talked about photodetectors. If there's an A in front of it, that stands for avalanche. An avalanche photodetector, you have a multiplication factor. So light comes in and generates one photoelectron, which, as we said, then that electron could go out and hit a speaker and you'd hear a click. But in an APD, they have increased gain. So before the electron comes out of the device, it scatters off of other atoms, generating more electrons. So here I have one electron generated by the one photon, might kick off two other electrons. E to the minus just stands for electron. It's particle physics notation, it means electron. E plus would be a positron. E minus is an electron. M is this increased gain factor. So you're going to increase the number of electron hole pairs per absorption. But that process, you can kind of see it right there. That's going to also introduce some randomness, right? You don't have any control, or you have limited control over when this extra scattering by the electron is going to occur. So that's going to introduce some noise, right? So APDs have higher gain, but they have more noise. Another little technology point that I want to sneak in here, I've mentioned a little bit before, but I want to do a cleaner version of it now. DFB lasers. DFB stands for distributed feedback. This looks something like this. Yeah, I could draw all this in Word if I had 1,000 more helpers, but I think I draw okay by myself. Anyway, here's an amplifier, right? Photon comes in, gets amplified, there's some gain G, so one comes in, two comes out, I've got an amplifier, right? But rather than putting my mirrors on the edges, like I said, a DFB, distributed fiber Bragg grating, is something you're familiar with. Those work like mirrors. Okay. Instead of putting my mirrors at the edge of the gain medium. Okay. This was the first way people built laser diodes, or lasers, that we use in telecommunications. But in this old way, you've got the mirrors at the edge. That creates these longitudinal modes like I drew before, and here I'm drawing more beautifully. Just like plunking a guitar string, there are all kinds of different oscillations that can happen here, right? The mirrors are a boundary condition. It's like putting down the fret and the finger on my guitar string. I can plunk that and get one mode to vibrate, but higher order modes could kick in too. And so here are all the different resonant frequencies that could happen in this type of structure. When I put mirrors around the edge of a gain medium, these mirrors form a cavity just like blowing across a soda pop bottle. You can have all these harmonics, and if you want to do a term paper on that or something, these are called Fabry-Perot modes. That's Fabry, P-E-R-O-T, is the fancy name for which we refer to such a simple structure. And the spacing here is set by the speed of light divided by the length of my gain medium, the length of my laser diode here, right? So in this old way of doing it, you excite these longitudinal modes. So I've got a whole bunch of different frequencies, right? What's the problem with having a whole bunch of different frequencies? Dispersion doesn't like it, right? Is more. Dispersion is more of a problem. Now, in the coming lectures, I'll try to get you some pre-lecture notes so you can draw along with it But just in this warm-up one, we're not doing that. Okay, so the old way had longitudinal modes, and so therefore we've got more of a frequency spread, right? Effective spread in frequency. Whereas the DFB lasers don't have that, so everybody's using DFB lasers these days. Another thing I wanted to make sure you had a nice clean picture of in your lecture notes. We've already talked about this, so let me say recall. We saw that by introducing more levels, you could have a higher data rate in the same frequency bandwidth. Right? Almost seemed like something for nothing, but the trade-off here, you can see, all right, if I've got binary AM, then 2 levels, here's my 1s and 0s, okay? Sorry, 1s and 0s. And my signal has a constraint on it, and the width of my pin mark is like the noise. Right? So I put in 2 more levels. I've gone from binary to 4-level AM. So look at the data rate there. That's one of 4 things would be 2 bits of information every t seconds. I just doubled the number of millions of dollars a month you could make in the same frequency bandwidth, right? Because frequency bandwidth doesn't depend on, that's separate than the data rate. Frequency bandwidth always goes like 1 over capital T. Capital T is the distance between the bits. Right? The distance between the pulses, the distance between the sample times, in other words. Right? And of course we'd love to boost up the signal, but you run into nonlinearities. Of course, reducing noise is always a good thing, but how are you going to reduce it? If it's thermal noise, you have to cool things, then that's very expensive. So at some fixed signal to noise ratio, putting in more and more levels is going to cause more and more bit errors. I start to get confused, right? When I cram all these extra levels in here, what's happening? I can't tell one from the other, and I start to make mistakes, right? So, another way of saying that is that the bit error rate goes up, right? The bit error rate, abbreviated BER, is also equal to the probability of making an error, right? So we have these bit error rate curves, okay, which plots the bit error rate versus signal to noise ratio. Binary AM is the lowest here, right? Because when you start to introduce more and more levels, or likewise more and more states, they don't have to be levels. Could be like 8 PSK is 8 different phase shifts. These are called signal constellations. So PSK stands for phase shift keying. Obviously I have to know the phase here, right? The difference between sine and cosine. There's a 90-degree phase shift between the two. With 8 PSK, then I've got it to know the phase even more accurately. Put in more dots and it becomes even worse, right? So clearly at some fixed signal to noise ratio, putting in more and more states is going to increase the bit error rate. So that the higher level modulation schemes are going to have bit error rate curves that are above the binary AM curve. Okay? So we went over all that before. I just wanted to give you a nice clean version of it. And another thing that we kind of did on the board one day was, all right, use that same curve, but look at it in a different way. Instead of slicing along the x-axis, slice along the y-axis. Then instead of fixing the signal to noise ratio, you would be fixing the bit error rate. Bit error rate is like quality of service. Right? For example, bit error rate of 10 to the minus 3 means on average 1 out of every 1,000 bits is a mistake. That's starting to get annoying even if it's just a telephone call, right? If it's a banking transaction, that's disastrous. So in the Bell system, the thresholds for switching out of that channel, rerouting the traffic, doing something for pure voice video, it was 10 to the minus 3. That was said intolerable. You'd switch out. That was the quality of service, in other words, that you wanted to guarantee to your customers. Right? It's going to be at least 10 to the minus 3. For raw computer data, of course everything's digital, everything can be thought of as data these days, but by computer data traffic, people mean this is like a banking transaction, is a good way to think of it. It's sending those numbers, and the numbers have to be more accurate. Then the threshold at which you would reroute traffic might be a bit error rate of 10 to the minus 6. 1 in a million bits is going to be a mistake. Okay? So if binary is down here, then 16 QAM, of course, would be above that. And reminding you, QAM stands for quadrature AM. There's a sine part of the wave, and there's a cosine part of the wave. If I had 4-level AM on one side and 4-level AM on the other quadrature, then 4 times 4 brings me up to 16. So I'm going to show you an example of how those modulators look, what they look like in a moment. But here's something that we discussed in the wireless course. If I'm closer to the radio tower, or wireless access point as they're called now, but it's a radio tower, right? If I'm close to the tower, then I've got strong signal, right? Because the signal drops off as I move away from it. So up here, I have a higher signal to noise ratio. Then with a higher signal to noise ratio from the bit error rate curve, you can see that I can guarantee same quality of service, but with a higher signal noise ratio, I could up you to a higher level modulation scheme, which increases the data rate even within the same fixed frequency bandwidth. Right? If I'm further away from the tower, then I've got less signal to noise ratio. So I might have to back you off, back down to binary AM at that point. Okay? So people do that in radio all the time. They're starting to try to do that in optical. And so that was the point I wanted to add here. Likewise, in optical, if a packet doesn't have to go as far through the network, then it's going to have higher signal to noise ratio. And so I could switch you up to a higher level modulation scheme. Right? Kind of a neat idea. And can go to higher level modulation, therefore higher data rate. If packet doesn't have to go so far. So those techniques would, be another good term paper topic. We'll talk more about term paper on Tuesday live, Tuesday Night Live. So if the packet doesn't have to go so far. Okay. So another little extra bit of information I wanted to get out there in the lecture notes is, well, how do you build some of those higher level modulators, and how do you demodulate that on the other end? Okay, and I'm stretching my neck to see, yeah, it almost fits. Okay, there we go. All right, so say I have 4-level AM signal, right? And in a normal radio system, and optical works just like radio, I'm going to take this baseband signal, your voice telephone, your ones and zeros at lower frequency, and I'm going to hit them, I'm going to multiply them up in frequency. So there are these devices called multipliers. And when you take one sine wave and multiply it by another sine wave, you get the sum and the difference frequencies. So the difference frequency you throw away and you send out, or you keep it, but anyway, you've modulated it up to the frequency of the local oscillator. I'm going to call that omega sub C. For example, in digital radio DR6 in the Bell system, the 6 stands for 6 gigahertz. So omega is 2 pi times F. From 6 gigahertz. Gigahertz is 10 to the 9 hertz. Wi-Fi is at 2.4 gigahertz. So instead of 6 here, it'd be 2.4. That's the carrier frequency. That's the frequency at which the radio wave is carrying the information. And so I would simply send that out the door. This symbol is to represent transmitter, right? This abbreviation is transmit that. Think of it as kind of like an antenna, right? Now at optical, it doesn't have to be an antenna. This is now a fiber, right? But I take your phone calls and I bring them up to some carrier frequency, the one corresponding to 50 and 50 nanometers, if that's the color I'm at, right? So I have this oscillator that just, all it does is it oscillates at that frequency, whether it's 6 gigahertz, 2.4 gigahertz, or the speed of light divided by 50 nanometers, right? It's just an oscillator. It's called a local oscillator because it's here. It's local to my transmitter. Now in QAM, I take advantage of the fact that if this is cosine, then hey, I've got this, it's like another polarization. It's like another channel for free. Take that same local oscillator, take that cosine of whatever frequency I'm at, shove it through a 90-degree phase shift box, and I just turn cosine into sine, right? And for historical reasons, they call this the in-phase quadrature and this the Q-phase quadrature. But these are like two separate phone calls. So think of this as your phone call and my phone call. Of course, they could be your channel and my channel, and you could be a whole set of companies or whatever. But you can think of it as like this message and that message, right? When I transmit that, now I've got, like I said, the signal constellation here. Let's draw that. On the cosine, I've got 4 levels. So instead of just plus or minus 1, maybe I have plus or minus 3 as well. But likewise, on the sine wave part of it, I've got 4 level AM. So draw out all those possible states I could be in, and 4 times 4 gets me 16 QAM would be my signal constellation, because these were 4 level AM. So 4 times 4 giving me my 16, right? With me? Cool. All right, on the receiver side, I can only do that if I can undo it at the receiver. Okay, so let's call this I data times cosine plus Q data times sine. I don't need the omega t's, you know what I mean. So at the receiver, in comes that same signal, I cosine plus Q, writing on the sine wave part of my carrier frequency. Then what I'm going to do is I'm going to split that into two copies. So this is a splitter, right? We know what those are. But the 0 degree splitter means if this one's cosine, that one's cosine. In other words, the two outputs here of my splitter are in phase. So here I have a copy of that same signal. I times cosine plus Q times sine. Here I have the identical I times cosine plus Q times sine. Right? Here I have another local oscillator at the same carrier frequency. And so it turns out that if I have one sine wave times another, I get the sum and the difference frequencies. So on one of these, I'm going to get twice the carrier frequency. Right? That's going to get filtered out, and the other one's going to bring me back down to baseband, back down to near zero frequency. Okay, so this was writing at 2.4 gigahertz. You hit it with 2.4 gigahertz, and now it's back down to where you can hear the phone call. But in QAM, make it so that this one's cosine, then put that through a 90-degree phase shift, and this is then going to be at sine. Then what happens is that if you do a time average, sine and cosine are orthogonal signals. If you already know what that means, then that helps. If not, then just think of it this way. Cosine times cosine, take the average of that, that doesn't go away. Cosine times sine, it does go away. So out here would come just I. And likewise, sine times sine gives me something, but sine times cosine, the average of that gives me 0. So out here comes the Q data. Okay? In other words, we said the I data was going to be your phone call. So here's your call. And here's my call. Okay? Now, what am I assuming here? I'm assuming that this thing, LO, stands for local oscillator. Local means it's here, right? If this is my cell phone, it's inside my cell phone. Right? If this is at the radio tower, it's inside the radio tower of the building. How does this oscillator know what time it is compared to this other oscillator? Right? They can drift. They can drift in phase. They could also drift in frequency. How do you know it's 2.4 gigahertz? That little oscillator has a crystal or something that makes it at 2.4 gigahertz. When you change the temperature, it's going to shift a little bit. Okay. So the hidden bits here are that my local oscillator here has to be driven by something more complicated. This local oscillator here has to be set set by information. In other words, there's two things I really need here. One is that frequency. And the other is that phase. Okay. So there's some fancy circuit that tries to figure out, well, what exactly is that frequency that's coming in? Is it 2.4002 gigahertz or is it 2.4003 gigahertz? Right? That's locking in the frequency to be exactly the carrier frequency of the incoming signal. The other is, well, if that's not cosine, if that turns into sine, then instead of giving you your phone call, I just gave you my phone call. Right? I'm going to mix I and Q, or you get half of one, half of the other, or some other mixture. Right? So it can only work if I can tell this local oscillator what's the phase compared to what it was at the transmitter. Right? This is called a carrier recovery circuit. It's complicated. Okay. Likewise, it has to work the same way in optical. That's why optical started in a more simple way. Optical started with just binary AM, and it doesn't care about the phase. Right? But we know we can beef up to higher data rates by going to these phase-dependent schemes, which means it's so-called coherent, as we said. Phase-dependent, we call this coherent. So when you talk to Sienna and they're trying to sell you some coherent, this is the latest, greatest thing. That means it's some type of phase-dependent modulation scheme. QAM being one example that I've drawn out here in great detail. Phase shift keying obviously depends on the phase too, right? So there's got to be something that sets an equivalent phase of my local oscillator in a PSK system as well. Oh, see you next recording.